Hi, everyone. Thank you for attending my talk. I'm very happy to be here. I'm Jason Cohen, the founder and CEO of Gastrograph AI. My talk is on how we can use consumer preference modeling to create new food and beverage products and push the industry of sensory science forward. And so it used to be that the hardest problem in CPG was scale and distribution, being able to create a product and distribute it and get it into consumers' hands. Was something that companies gained a competitive advantage. Having massive scales of distributions, recognizable brands, being able to move products around the world was a competitive advantage within the industry. And the tools that companies used in order to develop products that were expected to be generally acceptable, were things like professional panels, where you had individuals formulating products based on their own preferences and their own tastes, and consumer panels, using consumers in order to determine consumer guided feedback or which products were going to be generally acceptable. And all of these tools were geared towards making a singular product that everybody liked. But today, the hardest problem in food and beverage is the ability to create targeted and competitive products. Today, there are hundreds of products that are each a better fit for a narrower consumer demographic than any one product can be a fit for everyone. And so we see Coca-Cola losing a couple percentage of sales year on year. We look at the kombucha shelf and we went from maybe 5 flavors or 10 flavors, and now there are 20 or 30 flavors on the shelf. And it's because individuals expect to have products that not just they like, but products that meet their preferences and that they love. A product that feels as if it's made for them. And traditional methods aren't built to solve this problem. And so once again, I'm Jason Cohen, founder CEO of Gastrograph AI. We're using contemporary cutting edge techniques of machine learning artificial intelligence to help companies develop products that consumers are going to love. And part of the way that we do that is by entirely separating perception and preference. So our artificial intelligence platform models human sensory perception of flavor, aroma, and texture in order to predict consumer preference of food and beverage products. We help predominantly large food and beverage companies develop new products, optimize existing brands, or enter new markets, all from the perspective of making better, more targeted flavor profiles for consumer demographics around the world. And so the way that we do that is by modeling perception and preference entirely independently. So first we model what any given consumer demographic or consumer cohort, what they perceive in a product. And we can do that across a variety of different demographic factors, things like age, sex, race, socioeconomic status, past tasting experience, and smoking habits. And only when we've parameterized for what they're perceiving in the product do we model their preferences today and predict the evolution of their preferences into the future. And the reason that this is possible is because in the last 10 years of data collection, actually now probably 12 years of data collection, started in 2009, we've collected the world's largest sensory data set of on-market products. We have individual teams, both in New York and Shanghai, constantly profiling products. And we have an additional team, our forward deployed tactical global panel team that circles the world, recruiting consumers, having them taste 80 to 90 products before moving on to the next city or the next region. And we've been doing that, as I said, since about 2009, collecting this data. All of that data that we collect goes into our trunk. This is our proprietary data set that we use in order to build our baseline models. And then any data that's put in by one of our customers goes into their branch. So we work on a trunk and branch model. And as I said, this data has been collected now in more than 30 countries, more than 45 regions. Our data collection happens in more than 22 languages around the world. And so the way that it works, the way that we're able to make these predictions, I'm going to jump into a little bit of the technical specifications, and I'm going to move to a variety of case studies. What we can do is we can take data from any given demographic, from any country or any given demographic, and we can translate it to any target demographic. So just like Google Translate can translate French into Italian or Italian into Chinese, we can take data from, say, white 20 to 30-year-old college-educated males and translate that into what any other given consumer demographic perceives in a product. And so I'll use this example. What we're actually doing is we've trained the AI on a form of demographic translation using metric learning. So we are predominantly a topology shop. In this example, let's say we have three different demographics: triangles, circles, and squares. Triangles could be Americans, circles are British, and the squares are, of course, Germans. If we're interested in predicting what the German demographic would perceive in this product, what we can do is take all of our triangle and circle data and translate that to the German perception. And what that gives us is a more robust distribution for how that demographic tastes and a higher resolution to exactly what they're tasting. And so once we have this translation layer built, we don't actually need the target demographic on the panel anymore. We can take all of our triangle and circle data and we can translate that to the square perception, and we can predict what the German population would taste without having any German individuals taste it. And so we, in fact, can do this across, like I said, age, gender, race, socioeconomic status, past tasting experience, and smoking habits. So we can target any number of different sub-demographics that's of interest for a company. And we can do this without any repeat testing. And so what that leads us to is the value of a predictive framework, moving sensory science, moving consumer research from an empirical science where you are running frequent statistical hypothesis tests based on experimental design, concerned about the power of tests based on the amount of data that you're able to collect, based on concerns around panel fatigue, palate fatigue. You can't have individuals taste 5 or 10 or 20 products in a day because of fatigue rates, ordering effects of those products, right? And moving that into a predictive framework. And what that predictive framework does, what our system does, is one, everything that we do is predictive. So we're entirely Bayesian in philosophy. We're collecting data, we're using that data in order to build models, we're updating the models as more data comes in, and we're actually able to use all of the data that we've ever collected in order and bring that data to bear on any new questions or new analysis or new predictions that we're making. The reason that we can do that is because the system is question agnostic. So we're not running experimental designs, we're actually asking individuals, what do you perceive in this product? What do you perceive in any of these products in an identical data collecting fashion? So we have our own unique sensory system that allows us to collect that data. And so because of the predictive power and because it's question agnostic, what we can engage in is compound learning. We can consistently update our models, we can keep our models up to date with new collection. And in fact, our models on any given country are good usually for about 3 to 5 years, depending on when we collect the data and how quickly that country is changing. And what this leads to is more actionable insights than is possible with traditional methods. Traditional methods need to do things like difference testing in order to prove the products are different, or similarity testing in order to prove the products are the same, or stack rank preference tests in order to prove that one product is liked more than each other. But if any of those tests fail or you can't reject null hypothesis, right, then it is not proof of the contrary. You don't get a contrapositive result and say, well, these products fail the similarity test, they're not similar, that means these products are different. That is actually a different test in this field. And so using our methodology where it's all unified and you're not running experimental designs, we're actually able to make predictions for all of the standard testing that's done. We're able to replicate those results and we're able to exceed those results because the AI is able to answer additional questions that are not possible with traditional methods. And what that means is it moves us from a world of data scarcity, right? Where sensory data is slow and expensive to collect because it's dealing with people and you have to give people food and beverage products and you can only give them so many products. So you have to recall them day after day, right? And that data can only be used once because when you're in an experimental design, you can't reuse the results of that in order to generalize to future results. And so what we're doing is we're moving the world, this industry, this field, from a world of data scarcity to a world of data abundance, where we can reduce, reuse, and recycle that data, we can engage in compound learning, and we can continuously learn from that data over and over and over again as our models get better. And so really important, reduce, reuse, recycle. This is something that we say as a mantra here. We need to be able to reduce the total amount of data required in order to make inferences. So our models are trained on not truly big data, right? Our data fits in memory, but we have the largest sensory data set. We're able to make greater levels of model training. We're able to better improve our model architecture because we have the most data. But what that means is we can also reduce the total amount of data that we need on any given new product. So we're now actually able to make inferences on new products that the AI has never seen before, on just 5 to 10 observations, right? From any group of individual panelists. So one of the things that we always talk about is it's actually impossible at any given sample size when you're dealing with humans to have a randomly stratified, a homogeneous and IID population. Human population is not homogeneous. We're not independently and identically distributed. Sensitivity to flavor is not normally distributed throughout the population, and flavor itself is not evenly distributed across the world, which means that adaptation due to repeat exposure to flavor yields perceptual differences on a per individual basis. So what the technology actually needs to be able to do is build robust inference models across a non-randomized, non-IID sample. And our ability to do that is based on the demographic translation, which allows us to reduce the total amount of data that we need. Second thing is reusing that data. So let's say that a company wants to add additional products to a test or additional prototypes to say which of these prototypes are preferred. We're making a new product. I'm going to make a number of different prototypes. I want to consistently update the result to know which prototype is going to be preferred. Traditional methods can't do that. Here, there's no difference for us, right? Because we're running monadic testing, and we're able to update those results using all of our data and integrate new products into the analysis. We can do that not only for new products, but we can add competitor products. We can add variations. We can do scenario models. We can make algorithmic products, synthetic products, just based on the data in order to do that. So we can reuse that data for a number of different things. And in fact, we can bring all of that data to bear on relevant categories. So if one day we're working in white bread, that data is still usable when we move over to rye bread, and that data is still usable when we move over to sourdough bread. So we get much better data utility from these generalizable models. And finally, the third thing is recycling. Because of the demographic translation, if a company says, how would this product do in Spain? And we say it would do fine, it would do well, maybe it would do poorly. They can say, okay, now use that same data and predict how all of those products would do in Germany, right? And we can do that with no new collection because we already have a Spain model, we already have a German model, and we already have data of those products. So this framework is a very powerful framework. And we think that reduce, reuse, recycle is something that's actually generally applicable, right? The ideas of moving from data scarcity to data abundance, the ideas of reduce, reuse, recycle, this is something that's generally applicable across a variety of different machine learning and artificial intelligence technologies across a variety of different industries. So we'd be very happy if anyone else feels inspired about this. And it brings this framework, this idea to bear on your own problem space. So let me show you a little bit about how this works in action. I'm going to run through two different case studies. The first is high preference whitespace optimization. So how do we create a new cola, new flavors, no competitors? It needs to be full sugar, which means that it's not going to be a diet. It's not going to have any of the funky gamey flavors that come from high intensity sweeteners or diet sweeteners. And we need to be able to do this, no new data collection, right, on the same day of the request. And so what the AI came up with was actually a toasted malt cola, right? That's a novel flavor combination. It's in a high preference white space, so it's liked by consumers and there's no competitors. And we were able to develop a detailed profile for that. And the way that the AI found this is by iterating through thousands of signatures that it had seen across the world in different contexts and different application, right? It saw ginger in North America and Asia. It's seen coffee in South America, North America, Western Europe, Asia, and Australia. It's seen cloves in North America, Europe, and Asia. And so it was able to bring all of these things together from across different contexts and across different products in order to predict a very targeted flavor profile around exactly what should change in order to make this product great. And if we look here, right, D at malt, it's moving D from 0 all the way up to 6% of the flavor profile for a whole 1 point impact positive on preference. And so this is just a singular example, but it's showing how the AI can come up with flavor profiles that no human formulator would ever think up of. So the next one that I want to talk about is market maps. And this is a great example of how having more data in a predictive framework can be used to build new features, new capabilities that have never before been possible. And so market maps are something that are relatively common within the industry. It's a way of displaying in 2 dimensions where products fall in a market. So if you want to take, say, all of the coffee in the United States, what does that coffee look like? How are the products different? What are the axes of competition? What are the things that are driving preference? Well, we said, what happens if instead of building up, what would happen if we were able to use, not just 10 products that are normally included in a market map, or not just 20 products, right? And maybe some companies out there have seen market maps with 50 products, maybe, right? But what happens actually if we were able to use hundreds of products, or actually thousands of products, or actually tens of thousands of products, and bring all of the data that we've ever collected to bear on this question? What if we reimagined what it meant to do a market map so that we were actually able to see all of the products across a market in one unified visual? And so that's exactly what we did. We brought all of the data that we've ever collected. I'm going to use coffee here as an example. This is instant coffee in the United States, flavored instant coffee with creamer. And we were able to bring that to bear. So the way that we read these maps is these are built up layer by layer. The first layer is preference. So red, obviously negative, green means more positive, white means unknown or unexplored space. And you can see that there's a competitive axis here, right? The products down to the bottom left are more preferred, slightly more preferred to the top left, but generally there's a large axis of dispreferred products. And on top of that, what we can do is we can layer in the market density. So where do these products fall in the market? Well, to no one's great surprise, bottom left, which is the most preferred, has the most products. That's good. It means that consumer preferences are being discovered and met using either our technology or traditional methods. But actually, if we look to the top right, we could see, and down that ridge on the right, we could see that there's actually quite a bit of products that do not fall into consumer preference. Okay, now on top of this, we can layer in the competitive axes, the axes that are driving preference and dispreference. In black, we have our vector space. Those are the main axes of preference, flavor that separate the space. And in blue, we have characterizing points. So we were able to pick out a pure flavor on these maps. These would be the pure flavors. And so towards the bottom left, we see things like retronasal, that's level of aftertaste. We see rich, that's things like cream and milk. To center left, we see sugar and cane sugar. And so what's driving preference here is sugar, rich, and retronasal. People like their coffee, instant flavored coffee. They like it rich, full of milk and cream. They like it sweet, cane sugar, and they like it to have a pleasant, strong aftertaste. Interestingly, what is not driving preference in this space is roasting coffee. If you look in between the dry on the top and the astringent on the right, that roasting coffee point and down to the right, bitter and raw cocoa, so chocolatey flavors, are not preferred. And that might be a surprise to many people. And finally, on top of this, what we can do is we can plot the points of products. So we can see here are 3 products that actually are on market and exist in this space, A, C, and B, and they are differentiated generally by the amount of sugar in them. Now, we can go one level deeper because unlike traditional methods, every single point on this map is actually a complete flavor profile. So if we look at point C, we can see the entire flavor profile on the inside this callout box. On the top left is the objective flavor profile, so the relative attribute magnitude intensities. On the right is distribution of preference. On the bottom are scenario models. So what would happen if they changed any one of these things? So if we look at C, which is milk chocolate, if they increased milk chocolate, they'd gain preference. On the right is the flavor profile decomposition. So these are the relative attribute magnitude intensities of each of the flavor categories and the specific flavors within those categories. So dairy is 27% of the flavor profile, of which 7% is milk, 6% cream, 5% caramel, 4% butter, so on and so forth. And so you can get a very high resolution view of exactly what's in this product and exactly what you can change. And not only can you do this for existing products on the market, but every single one of these pixels represents an opportunity. So we can arbitrarily pick any pixel on this map and we can see exactly what the flavor profile driving it is. And that might be a real product that we've collected data on that's on the market, or it might be competitive and interesting white space. It might be a totally synthetic flavor profile predicted by the AI into this space. And so you can discover new formulations that you would not otherwise have stumbled upon by using these maps, by using and leveraging all of these data to create this map. So last thing that I want to talk about on these maps are the scenario models. These show you very, very clearly what you need to change in order to bring your product into a more preferred space. So taking this product C, we can move it around this map. We can do constrained optimizations or we can do univariate optimizations. And these curves will show you the scenario model of what you should change to bring it into a higher preference space. And so what I hope these two case studies show is how we can build a predictive framework around profiling product and predicting for consumers, and how leveraging all of this data and using this predictive framework allows us to accomplish things that are impossible without the application of machine learning and AI. So once again, I'm Jason Cohen, founder CEO of Gastrograph AI. Super happy to discuss anything that I've mentioned here, and I'm looking forward to talking to everyone. Thank you.